Hello, welcome back. Today, we're going to talk about the basics of hypothesis testing. So our goals, understanding what hypothesis and hypothesis test are. They'll conduct a hypothesis test using a critical value method, or more importantly, the p-value method. This method will focus on and understand the difference between type 1 and type 2 errors. We'll explain all that. Let's take a look first at a hypothesis, what it is, and kind of explain how we're going to use it. Let me just read this part. In statistics, a hypothesis is a claim or a statement about a property of the population, such as a parameter, such as the mean or the proportion or standard deviation, something like that. And basically, we'll see claims. Our focus is going to be on the claims about the following parameters, about the population mean, mu, and basically to tell which one it is, if we see a word like the average or something, that's going to be the mean, and also the population proportion, p. So I won't talk about average. We'll talk about like a proportion or percentage or something like that. Now, a hypothesis test, sometimes called a test of significance, is a procedure for testing a claim about a property of a portion, such as the mean or the portion. And we'll need to form a complete hypothesis test for claims to understand the process. So let's take a look at an example. We're not actually going to work, was kind of explain a type of problem where we actually use these ideas. So let me read this. It says, the state of Tennessee is considering funding fast chargers for electric cars throughout the state by raising taxes. And actually, I made this example up. I'm not sure not claiming this is true. The governor believes that more than 50% of Tennesseans should approve before considering the idea further. To test the idea, they make a claim. More than 50% of Tennesseans approve of raising taxes to fund fast chargers for electric cars. To test this claim, they complete a survey of 1,000 random Tennesseans and find that 57% favor raising taxes to fund the building of fast chargers for electric cars throughout the state. Use a 99% confidence level to test this claim. So this is the kind of problem we want to be able to solve and do a hypothesis test to answer. So in this one, the idea is that we have a claim. More than 50% of Tennesseans approve of raising taxes to fund fast chargers for electric cars. So that's our hypothesis. That's a claim we want to test. And so what we want to do then is, using the sample we mentioned of 1,000 random Tennesseans, we want to be able to use that sample, and from that sample, use statistics to indicate whether or not that this sample is likely, or how likely the result is. So let me say it this way. So the idea is that the claim is more than 50% of Tennesseans do favor this. So we're going to break our hypothesis down into two parts. One's called what's called the null hypothesis, which is kind of the sometimes called the hypothesis of no change or no effect. So in that, we'd simply say we need to compare it against what's called the research or the alternate hypothesis, which is the claim we're stating that more than 50% of Tennesseans do approve. So we need something to compare it against. So our two hypotheses would be that the null hypothesis would be that essentially there's no effect, no change, or that basically it's the percentage of Tennesseans who approve is basically 50%. Not so much claiming that's the truth, but to compare it to the actual claim that's greater than 50%. Then with a sample, the question is, the result we got is 57%. So if we assume that basically 50% of Tennesseans, only 50% favor this, how likely is it to get a sample where we get 57% favoring like this? And we can actually calculate that statistically. And so the question will be, if only 50% of, if no more at least, than 50% of Tennesseans actually favor this, and we got this sample of thousands random Tennesseans saying 57% favored it, how likely is it that, if that's a really unlikely outcome, the sample result, then what's more likely, that we just got a really unlikely outcome, or that actually more than 50% actually favored? As that's kind of the idea of a hypothesis test, and these ideas will be more clear as we do this further and look at more examples. Then finally, this confidence level is the amount of confidence we're going to use. It's that statistical confidence. There are other kinds of confidences, and that doesn't count for all the kinds of error or everything that could cause problems, but just from a statistical amount of confidence, that's what we use. And that's also a choice. Okay. Now, let's move on. So we got the idea of hypothesis about. So let's talk about our hypothesis or procedure to test hypothesis. So I'll break this down into steps. Our first step is find the claim statement. The one we just did, we found that. Yeah, often there's actually the word the claim in it. Okay. Now we want to create what's a null hypothesis. Okay, which in our case will be equal to some value. And it's not so much saying that we believe it is. We'll explain that further. As much which we believe this null hypothesis is actually equal, is you need something to compare it to against the what's called the alternate or research hypothesis. And basically, the alternate hypothesis is usually going to be stated either in greater than some number, less than some number, or not equal to some number. So the null hypothesis for our purposes will be equal to some number. And basically, we're going to make these claims about either population mean, mu, or population proportion, p. Okay, now this is going to be some claimed value. And it says be careful to make the error using the sample data when you set up the alternate hypothesis. We're only making claims about proportions themselves, not about the sample. Okay, so let's take a look over on the right at some examples. We're just practice with this idea of creating a null and alternate or research hypotheses. Let's take a look at each one. So we want to basically create these two hypotheses in each case, and then also use the correct values. The owner of a football team claims that the average attendance at games is over 68,800, and he is therefore justified in moving the team to a city with a larger stadium. Okay, now, so our claim then is made by the owner. It says the average attendance of games is over 68,000. So when we're looking at, we're talking about an average. It says the word average, talking about a mean, and its average is over 68,000. Okay, so then our null hypothesis is going to be our what's called our H0, and that's going to be well, actually, maybe easier to first write the alternate hypothesis, or something's called the research hypothesis. Let's review this for alternate. Okay, that's usually the claim. In some cases, the claim can be the same as the null hypothesis, but in most cases, the alternate is the claim. So the claim is that, or in this case, we're talking about an average or a mean, so we use the Greek letter mu for average. And the claim is that the mean is greater than 68,800. Okay, that's our claim. So then our null is, this for our purpose, is always equal to something, so it's going to be equal to 68,800. And once again, we're not saying that necessarily that it was, our test will show that it's definitely equal to one or the other. But just this is we need something to test the claim against. And so basically, if it's not greater than, it's at least be equal to or less than. So we're choosing equal to. Okay, here, that's all we're doing is setting up our hypothesis. So this is the hypothesis we're testing, and then we use a statistical test, in this case, determine how much evidence we have this is true. Okay, next. A skeptical paranormal researcher claims the portion of Americans that have seen a UFO is less than 2 in every 1. Oops, sorry, that's actually a typo. That's a 2 in every 1,000. Hang on, let's see if I can. Well, so that should be 1,000, 2 in every 1,000. Or let me just erase that, just call it 2 in every 1,000. That'll work. Okay, 2 in every 1,000. Okay, all right, so once again, the null hypothesis is our H0. Now this time, what are used, is it a mean or proportion? Well, here it is a proportion. We're talking about proportion P. And then our alternate hypothesis is called H1, or sometimes called HA. You may see that occasionally as well. Some call it HA, since once again, this is our null hypothesis, or hypothesis of no effect, and this is our alternate hypothesis. So we're both making claims about a population proportion. Now, sometimes it's easier to do this one. Also, 2 in every 1,000, that would actually be then, so this time it says less than 2 in every 1,000, so it's less than, and that would be 0.002. If you divide 2 by 1,000, you get this. It would be less than that. So once you have the claim, then the null hypothesis is actually a lot easier. Just make that simply 0.002. Then hopefully we have some data to compare this and do statistical tests to see, if there's evidence to support the claim or not. Okay, keep going. The manufacturer of a refrigerator system for beer kegs produces refrigerators that are supposed to maintain a true temperature of 48 degrees Fahrenheit. Ideal for a certain type of German Pilsner. The owner of the brewery does not agree with the refrigerator manufacturer and claims he can prove that the true mean temperature is different. Okay, same thing. Let's find our null and our alternate hypotheses. Once again, null we call our HO, alternate we call it either H1 or HA. Now, are we talking about a mean or proportion? Well, this time it says the mean temperature, so we're going to talk about a mean. So we use the Greek letter mu for mean. Now, this time it says it doesn't claim it's greater than or less than equal to this temperature. He just claims that it's different. So what does different mean? Well, different would be then not equal. Okay, so not equal to 48 degrees Fahrenheit. And then the null hypothesis is simply that it's equal to 48 degrees Fahrenheit. And that's it. So then in this case, we've seen a few different examples where you have greater than. So our alternate or null or research hypothesis can either, so in this case, for what we're doing, our null hypothesis will always be equal to some number. The alternate will either be greater than, less than, or not equal to, depending on the way the problem is stated. Okay, number 4. A researcher claims that 62% of voters favor gun control. Same thing. Let's set up our null and our alternate hypotheses. So once again, the null is called H0, and the alternate is called either H1 or call it HA this time, just so you can get used to that. Now, we're talking about a mean or proportion. Well, it doesn't use the word mean or average anywhere, and also it gives us a percentage. That's usually an indication of proportion. Also, if we were going to percentage, also want to write that as a fraction or a decimal. Okay, so proportion, it says, claims that 62% of voters favor gun control. And this is one where it's a little bit, the setup is basically identical to the one we just did, but the statement is a little bit different. So actually, our this time, our claim would actually be equal to some numbers. This time, our claim would actually be the same as the null hypothesis. It's a little bit different, but the setup is essentially identical. So researchers claim that 60% of favors gun control, and also doesn't say greater than or less than. So in that case, in the case of equal and not equal. Okay, so in this case, then the alternate research hypothesis would be that it's not equal to 62% or 0.62. And then you can see if the data reject the null hypothesis or support the alternate hypothesis. Okay, one more example. So you're kind of getting the feel for how to write these hypotheses. A cereal company claims that the mean weight of the cereal in its packets is less than 14 ounces. It's the same idea. So let's write our null and our alternate hypotheses. So the null is called H0, and the alternate is called either H1 or HA. Now, this time it says the word mean, so we're talking about an average. So we'll plug in our mean. Okay, let's do our alternate first. So it says the weight of the cereal packets is less than 14 ounces. So it's going to be less than 14. And then the null then is just going to be equal to 14 to compare it. Okay, so that's a little practice then in finding alternate hypotheses. Okay, now the next idea then is that's kind of how we set up our hypotheses. The next thing is actually to test these hypotheses. So do statistical tests to determine if there's enough evidence supporting one or the other. Let's take a look at that. So if we're testing a claim about a proportion, we're actually going to use a z-statistic or z-stat. It's look like this. And if you've seen previous videos for test statistics, you may have seen this before. So it's going to be set in the form of a z-score. So we have our p hat, which is our sample proportion, minus p, the assumed population proportion. And that proportion is what we're going to use in our null hypothesis. Okay, so this p you see here, this p without the hat, so the p hat is your sample portion. The plain p is the one's always used in our null hypothesis. We're assuming that to be true for the test, for the sake of the test. And here we have p again, the p in the null hypothesis, and q, remember q is 1 minus p over n, where n is your sample size. And this is valid as long as n times p is greater than or equal to 5 and n times q is greater than or equal to 5. That just means we can use, instead of the binomial distribution, use a continuous distribution like a normal distribution. Is close enough. In almost every case, it will be. We're using sample sizes that are large enough. Now, if we test a claim about a mean, we're also using a z-score. And actually use a couple of different ones depending on our circumstances. So if it's a problem with a mean like this, then in this case, if standard deviation is not known, we use a t-statistic. And here the x bar is our sample mean. Mu is our population mean, the one we assumed in our null hypothesis, just like this. S is your sample standard deviation. Then n is the sample size. Now, this is valid, as it says, as long as population is normally distributed or when n, our sample size, is greater than 30. Now, in the rare cases, this would be rare if the testing claim about a mean and the standard deviation is known. That would be rare. But if we do know the mean, then it's an identical test statistic, except we instead use the population standard deviation here. Okay, and once again, this is also true. The population is normally distributed, or when your sample size is greater than 30. The test statistic is a value we calculate then based on our sample we're given. Now, that's only part of it. What we also have to calculate then are what are called either critical values or p-values to compare the test statistic to. Okay, so explain these, and then we'll draw some pictures, look at some examples, get an idea of how these work. So let me actually separate this. Okay, now let's talk about the critical value method first. Now we're going to focus more on the p-value method, but the critical value method is also a legitimate method. Okay, there are two general methods we're going to use. What's called the critical value method. So if you have a significance level, such as an alpha, like this compares to confidence levels, there's an alpha of 0.05, which would correspond to a confidence level of 95%. We're going to find what we call the critical value or values for alpha in the appropriate table using technology. And basically, these critical values then are used, basically are dependent on what this alpha is. Okay. Now, then the test statistic is outside of the critical value, basically further from the mean than the critical value, we reject the null hypothesis. Let's take a look at kind of get an idea of how this works. A critical value method. Okay, and for our example, let's say we have a 95% confidence level. And if you recall, a 99% confidence level, that means that our alpha is going to be, if we convert that to a decimal, is 1 minus 0.95, which is equal to 0.05. Okay, now, then depending on the type of hypothesis, null or alternate hypothesis we have, we set it up differently. Okay, let's say our alternate hypothesis is that, and this works for either proportions or means. Well, let's just use a p. Okay, let's say our p is less than some value. Okay, then what we have is something that looks like this. So we're going from a z statistic, going from a normal distribution. Of course, here's the mean in the middle. Okay, then over here, somewhere over here, then we'd have what's called the critical value right here, and this separates this section right here, and this section here has an area of 5% or 0.05. Okay, so the way to think about it, if it's less than, then your critical value is points in that direction. So here, and this is what's called the rejection region. Okay, so what happens if our test statistic, our z-score, if it falls, the one we calculate, so let's go back here, we calculate this test statistic for proportion or mean, but any of those. But if it falls here, and falls in this region, in other words, it's further from the mean than the critical value, then we reject the null hypothesis. Okay, we say we reject the null hypothesis. We'll talk more about that concept in a moment. We reject the null hypothesis in that case. Okay, now, what happens if the H1 looks like this, and maybe its P is greater than some value, then it's basically the mirror image of this. So once again, we have some normal or Z distribution, or the mean. So over here, once again, somewhere, we'd have our critical value. And once you find the critical value depends on what the alpha is. You define that from technology or from a table. And this area, once again, so this should be the same image just turned around, although my drawing doesn't show that exactly. This area here is also alpha 0.5 or whatever your alpha is. Okay, then once again, we do our test statistic. And if that value ends up in this region or to further from the mean than the critical value, we reject the null hypothesis. Okay, then one last case, we said the other possibility for a null hypothesis, or sorry, alternate hypothesis, was that it was not equal to a number. Okay, so not equal to a value. Now, in that case, then what we have is we have two rejection regions. So once again, this is also a rejection. That's what's called a rejection region. Because if the test statistic is in that region, we reject it. Okay, this time we have two rejection regions. So we split the alpha in half. So you have two critical values, one positive, one negative. In this case, this is alpha over 2, which would be 0.025. Okay, half of that. And the same over here. This would be alpha over 2, which is 0.025. Okay, and then once again, this should be symmetric, and it's half the area. Each one is half the area. Each one these areas together, these rejection regions. Okay, rejection regions then would add to 0.05 or 5%. Each one has 2.5%. And then if your test statistic ends up in either of these regions, then we also reject the null hypothesis. That's the critical value method. And then what you have to do then is, and you also have technology to do this for you, calculate your test statistic and also calculate this appropriate critical value. Now, let's talk about the other one, which is called the p-value method. And either one is a legitimate way of doing it, just does it slightly differently. But I'm going to focus more on the p-value method. So let's take a look at that. Okay, and the p-value method, the p-value is a region outside the test statistic. Okay, I'll read this. It consists the value is more extreme, further from the mean than those of the test statistic. Okay, and then we find the p-value using technology, and then if the test statistic is smaller than alpha, reject the null hypothesis. Okay, so in the same way, our example, let's do a proportion again. So let's let's use once again an alpha of 0.05. Okay, and in the same setup. So if we have also an hypothesis that is once again use proportion, p is less than, or let's actually do a mean this time. So either way, it works the same way. We have a mean is less than some value. And let me just change it back to proportion. So everyone's clear that works either way, either case. Right, then what we have is once again either in both cases, either a normal or a, let's draw a better picture than that. Either a normal distribution or a t distribution. And it's not much better, but you get the idea. Okay, should be a standard normal distribution or a t distribution. Okay, so let's say our test statistic is right here. Or I'm sorry, well, not there. Since we're talking about less than, then our value would be over here somewhere. Okay, so right here is our test statistic, either a z or a t. Okay, and this area away from the mean, okay, more extreme, when it says more extreme than the mean or further from the mean, the test statistic, this little section right here is basically this area is the p-value. Okay, so this area, based once again, you find that with technology. This little area here is the p-value, and if that area is less than the alpha, then you reject the null hypothesis. So what you're saying is basically that both methods what are telling you, let's go back for just a second. I should have said this here, but the idea, the reason we're doing this is that we're trying to see, we want to see if there's enough evidence to support the alternate hypothesis. And the way to do that then is look at a normal distribution or t distribution and say that if the result we have from our sample is really unlikely, then to support it, it needs to be really unlikely. In other words, something's not likely to happen by chance. And so that's the idea of the critical values. Okay, we're picking some alpha, then basically it's got to be in this critical value. It's got to be something has a really small probability. It's not that likely to happen by chance. And the same thing with the p-value. Okay, in the p-value, you want to see if there's a probability that this value or value smaller than that are really unlikely to happen by chance. That's kind of this cutoff. And if that unlikeliness, that probability is less than 0.05 or whatever alpha is, then we can reject the null hypothesis. Okay. And in the same way, if we have our alternate hypothesis is that P or E or mu is greater than a value, it's the mirror image of this. So once again, we have a symmetric distribution. And then over here, once again, here's our test statistic. And this is called our p-value, this region right here. Okay. Because if it's far enough over here, it's unlikely happened by chance, assuming the null hypothesis is true. So if it's smaller than alpha, we reject the null hypothesis. Okay. And then the final case then, the H1, the P or mu is equal or not equal to some value, to some number. And so just as we saw with the critical value method, and once again, we have our symmetric distribution, and then you have two values here. So you have a positive and a negative test statistic, or you use the positive negative value of it. Then you have two p-values. Okay. And essentially, kind of like the critical method, they add together. So in this case, we have to multiply, since it's metric, multiply each individual one by 2. And if that area, that probability is less than our alpha, 0.05 or whatever, then we reject the null hypothesis. And both these methods, what they're doing is trying to give statistical evidence that the value we got with our sample is unlikely to happen by chance if the null hypothesis is correct. Okay, because that's the idea of that's how we can reject the null hypothesis and to say that we can give some support to the claim. Okay, all right. Now let's keep going. Let's talk a bit more about this. And also I showed in here how we can actually use, and use this in a moment, how we can actually use Excel to calculate either critical values or p-values. I think I just do p-values rather. Okay, I just do p-values, how to calculate those. So if you're using either a z-statistic, either proportion or mean, or a t-statistic for a mean. Now, so once we've done either the critical value method or the p-value method, then what we have to do is decide whether or not to reject the null hypothesis. So let's talk about the idea of a null hypothesis and alternate hypothesis. So think about the American justice system, the way it's supposed to work. So you've heard the saying that we're presumed innocent until proven guilty. And so that's how the American justice system is supposed to work. Stray mark. So once again, the assumption, you're treated as if you're innocent, and then the prosecutor has to collect, or that has enough evidence to show that that assumption is most likely not correct. Once it's not a guarantee either way. If someone is convicted, it's not always a guarantee. Unfortunately, sometimes people are convicted who are innocent, and then sometimes innocent people who are guilty are not convicted at all. But the goal is to find enough. If the null hypothesis is innocence, then the alternate hypothesis is guilt, and you have to find enough evidence to indicate that the person is guilty. In other words, you have to find enough evidence to say, how likely is it that we have all this evidence if this person is guilty? The assumption is innocence. And so you're trying to determine if there's enough evidence to make it to say this would be really, really unlikely for this person, for this all this evidence to point in this direction of this person, that this person was innocent. Okay. It's another way of another example I give is, imagine you want to test a coin to see if it's a fair coin or not. So if you know, a fair coin would mean when you flip it, you should get basically an even number of heads and tails. Let's say you decide to flip the coin 100 times. Let's say your assumption is it's a fair coin. That's our null hypothesis. You flip it 100 times and you get, say, 55 heads. Now, you wouldn't expect to be exactly 50-50 all the time. So 55 is probably not that unlikely. You're probably imagining it's probably wouldn't be all that unlikely to happen. And that's probably not enough evidence to say for certain that the coin isn't fair. It doesn't say that it is fair, just saying there's not enough evidence to indicate it's not fair, not a fair coin. We still don't know for certain. Okay. But basically, we're going to stick with the assumption that it's fair because there's not enough evidence to say otherwise. But what if you flip the same coin, or flipped a coin, and you got 70 heads out of 100 flips? So that should be really unlikely. Like, the chance of that should be really tiny. if that is in fact a fair coin. So if you use the null hypothesis that the coin is fair, then the chances of that happening is really, really small. So what do you think is more likely? That you have a fair coin and something incredibly unlikely happened, or that it's actually not a fair coin? That's the idea of the null and alter hypothesis. Null hypothesis is basically no change or no effect, just like innocence. And then you have to, the idea is that there is enough support to indicate that the assumption of innocence or assumption of fairness is not true. So that's the idea statistically. Okay, now let's talk a bit more than this. So let's go back to what we're mentioning. So once you get to the point where you decide to reject the null hypothesis or not, then you have to determine, so if we reject the null hypothesis, we want to say something like, there's sufficient evidence to reject the null hypothesis, or there's sufficient evidence to support the claim. Okay, we're not claiming, we're not going to say this means that the claim is true, or this means the null hypothesis is false. We don't know that for certain. We're just saying that there's enough evidence statistically to support the claim or to reject the null hypothesis. Okay, if you fail to reject the null hypothesis, say something like there's not sufficient evidence to reject the null hypothesis, or there's not sufficient evidence to support the claim. Once again, we're not trying to say that the claim is not true by this. We're just saying there's not enough evidence to reject the null hypothesis, or not enough evidence to say that the claim itself is true. Okay, so a few more keys to understanding. Let me just read these. Rejecting HO, the null hypothesis, means that there's sufficient evidence to support the alternate hypothesis. These are equivalent. Rejecting HO and supporting H1. Those are equivalent. Once again, we're not claiming absolutely one or the other is true. We're just simply saying, or the alternate hypothesis is true. We're simply saying there's enough evidence to support it. If we don't reject the HO, it means there's not sufficient evidence to support the alternate hypothesis H1. So these are equivalent. Fail to reject HO, it means we do not support H1. Once again, we're not making a claim whether or not either one is true. We're simply saying there's not enough evidence to support the alternate hypothesis. Also we never say we accept the null hypothesis. We don't know that. We're simply saying there's not enough evidence to reject the null hypothesis. We either reject HO or we fail to reject HO. Hypothesis does not give us the evidence to prove that HO is true. This is not the goal of the test. It's basically enough evidence to support the claim. Okay. Then finally, our last thing you want to do is just state the conclusion in a kind of non-technical terms in a way that's simple to understand. Okay, because you may not, in your careers, you may not do statistics, but it's possible you might be in charge or work with a group where it does statistics, where it might be the person actually doing statistics may report to you. Then you have to report to someone else to explain the details. And so, or at least give a conclusion of what the evidence says. That's what we want to do this last step to make sure we can do that. Okay. And also this, I'm not going to go through this, but this kind of gives you in the notes a flow chart for the 5 steps using both the p-value method, and the traditional method is also called the critical value method. Okay, so you can look at that on your own. And then also let's go, before I get to type 1 and type 2 errors, let's do a couple examples, kind of actual examples, how this works, putting everything together. Okay, so let's say we have a claim, fewer than 95% of adults have a cell phone. A recent Marist poll found that of 1,128 adults, 94% have a cell phone. Use a 90% confidence level. Okay, let's put together a few things we know. All right, so we have 90% confidence level, so our alpha is going to be 1 minus 90% of the decimal, 0.9, and that's going to be 0.1. That's going to be our alpha. Okay, that's what we're going to use to compare. Now, also, what else do we know? Our N, our sample size, is 1,128. Our sample proportion, P, is 94%, or I'm going to use 0.94 as a decimal. That's what we're going to use in the problem. Then our Q, well, our P is that, rather. Now, make sure don't get these confused. Then the P hat, is the sample proportion, but the portion we're going to use in our hypothesis is going to be the population portion we're comparing it to, which is going to be 95% or 0.95. And then finally, our Q, which is 1 minus P, then is going to be 0.05. Okay, once again, be clear which one is which. So the P hat is our sample proportion, 94% of the sample, but the P of our population we're assuming is 95. Okay, now let's do our hypotheses. So our null hypothesis and our H1 or HA, our alternate hypothesis. So as we just did, we're talking about proportion. So we're talking about the population portion, P, not P hat. And our claim is that fewer than 95% have a cell phone. Let's use the decimal, so less than 0.95. And then our null hypothesis simply that is equal to 0.95. Okay. Now, I also need to find our test statistic. So let me go back in the notes. On the left side, what did I just do? Okay. I've seen that before. I think someone accidentally wrote. That somewhere. Okay. In fact, yeah, there it is for some reason. Okay. Let's go back and take a look at our test statistic. Okay. So for testing claim about proportion, here's our test statistic right here. Okay. So we're going to use a Z. So that's going to be Z and just fill everything in. So our P hat, our sample portion is 0.94 and minus our population portion, the one that's assumed in our null hypothesis, which is 0.95. Then divided by the square root of P, which is once again, this is P without a hat, 0.95, times Q, which is 0.05. Then that's divided by the sample size, which is 1128. Now, I've already calculated this, and it should be approximately negative 1.54. Okay. Now, we're going to use the p-value method. So what we have is from a symmetric or a normal distribution. And once again, here's the mean of that distribution. Also proportion, we're thinking about the sampling distribution, and this is the idea of the central limit theorem. Now, this Z value is way over here. So Z is equal to negative 1.54. And then we want to find this area to the left. Okay. This is our P value. Okay. That's what we want to compare. Now, to find that, we're going to use Excel to find the P value. Now, I gave you the instructions how to do that. We'll open up Excel and do this in a moment. So finding p-values in Excel, okay, for a Z test statistic, that's what we're looking at right here. Okay, now we follow this case. So in this case, the alternate hypothesis is H1 less than the value. That's what we're using right here. Okay, so when we plug into Excel, make sure you use the equal sign, is norm dot s dot dist. So that means the standard normal distribution. Then our z-score, or z-value, which is negative, or test statistic is negative 1.54. Then we use the word true, and that indicates we want a cumulative distribution. So let's go to Excel and do that. So once again, type in here. Make sure always use the equal sign. Then to start to type in, you get the different options. So make sure you choose the right one. And also, if you read it, it says returns the standard normal distribution, has a mean of 0 and a standard deviation of 1. Double click on that. Also tells you what you have to enter Z in cumulative. So our Z is, make sure you use the negative 1.54, and then the word true, and hit enter. And that is 0.06178. Okay, 0.06178. Okay, so that then is the area to the left of our test statistic Z. So basically, the probability of being in this region is basically that, about 6.1%, 6.2%. Okay, now the last thing we do is compare that to alpha. Okay, so here our p-value What can we compare to alpha? So the p-value which is equal to, I'm just trying to find the best way to write this. P-value, well, just simply is less than alpha. Remember what alpha was. So this is 0.06178. And alpha was 0.1. Okay. So that's clearly less. Okay. And so what's that means? So we reject the null hypothesis. So what this means is that there's enough statistical evidence to say to support the claim that fewer than 95% of adults have a cell phone. Okay. Now, the idea of this study, the idea of what we're doing here is that for comparison purposes, we're assuming for our null hypothesis that 95%, the value that adults do have a cell phone is 95%. That's more for comparison purposes, not necessarily that we automatically believe that to be the case or that should be the case. But we need something to compare it to against our claim the alpha is less than that. Okay. The other option would be less than or equal to that. And to say we just compare it to equal to, that will work. Now, so the idea here of this statistic is we're assuming for a distribution that p is equal to 0.95. Okay. What happens then, we did a sample and we got a fairly unlikely result. Okay. Probably only being about, at most about 0.62%. Okay. So the question is, what's more likely? That the actual mean is about 95% of people have a cell phone. And we got this sample of quite a few people, over 1,000 people, and got a really pretty unlikely result, or that the actual percentage is less than 95%. And that's what we're saying here is we're rejecting, there's enough evidence to reject the null hypothesis that the value is 95%. Okay. There's enough evidence to support the claim that the value is less than 95%. All right. Once again, this doesn't mean, and it's not a guarantee that we're right. In no way are we guaranteeing that we're actually correct about that. It's just simply there's enough statistical evidence to support the claim. Okay. It's possible that we could be wrong to support the claim. It may not be correct, but there's enough statistical evidence to do that. Okay. And then finally, let's make a quick statement summarizing this. I'll say a summary. Okay. And just say something like, there is enough evidence to support the claim. Either say reject the null hypothesis, support the claim, or something like that. I'd also like to say something about the confidence level. So at 90% confidence. Now, also one thing is worth mentioning, write the word confidence first. If we did a higher confidence level, then, for example, we did a 95% confidence level, so alpha is 0.05. In that case, our p-value would actually be larger than alpha, and we wouldn't reject it. So rejection also does, your confidence level does depend on, have an effect on whether you reject or not. Well, I'm just going to write that word better one more time. 90% confidence, or maybe just abbreviated. It's going to write too well tonight. So 90% confidence. There's enough evidence to support the claim that fewer than 95% of adults have cell phones, okay, with 90% confidence. Okay, let's do one more, a similar one. Now, according to a recent poll of 53% of Americans, sorry, let me start that again. According to a recent poll, 53% of Americans would vote for the incumbent president. If a random sample of 100 people results in 45% who would vote for the incumbent president, test the claim that the actual percentage is not 53%, use a 95% confidence level. Okay, once again, let's write down what we did before. So our alpha is going to be 1 minus 95% is a decimal, 0.95, which is then 0.05. Okay, our sample size is 100. And then look at our, also we say, that I should have said in the last one as well, how do we know this is a proportion or a mean? We're talking about percentages. And also the word average never comes up, so we're talking about a proportion. Okay, our sample proportion, P hat, is 45% or 0.45. Okay. Our population portion we're going to assume in our hypothesis is 53% or 0.53. And then finally, our Q is going to be 1 minus that, which is 0.47. Okay, 0.47. Let me write that just a bit better. No, I'm almost out of space over here. So 0.47. Okay. Now, once again, our hypotheses. So our null and our alternate hypothesis. Once again, we're talking about proportion. Now, of course, null is going to be equal to something. Now, let's see. So the claim is the actual percentage is not 53%. So it's probably easier to do the null hypothesis first, or an alternate hypothesis first is not equal to 0.53. And then simply or I can't write tonight, 0.53. Then the null hypothesis is simply that it's equal to 0.53 to compare. Now, let's do our test statistic. Just abbreviate that. All right, the same test statistic as before, the same z values. Let's go back and take a look at that. All right, so z is equal to our p hat, which is 0.45, minus 0.53, which is our assumed value over proportion. Then the square root of p, which is 0.53, times q, which is 0.47. This is all divided by the sample size of 100. Okay. Now I also calculated this. We can check on your own, and this should be approximately negative 1.6. Okay. Now, once again, we use a p-value test or p-value method. So if we draw this again, so going from a z distribution, a symmetric distribution, once again, here's the mean in the middle. And this is sampling distribution. So p, the actual p, should be right in the middle. Okay. Now, our z is over here, about negative 1.60. And once again, so our p value, now this time, since it's not equal to, we'd also have the corresponding z over here symmetric of 1.60. And once again, these should be a mirror image of each other. This should be the same over here. Okay. Now, this is our half of our p-value. This is over here. This is the p-value actually divided by 2. And this is also the p-value divided by 2. So we need to find our p-value. Okay. And once again, we use Excel. Okay, let's go back over here and see how to do that. Okay, a little bit more involved this time, but let's talk about it. Okay, so it says we're going to plug in this is equal to 2 times, then in parentheses, 1 minus that same function again. So norm dot s dot dist. Notice it also says here, this is the absolute value of your test statistic. So I'll use the positive value. Okay, doing this as a 1.60, and then true for the last part. Also make sure you close the parentheses. So let's go back to Excel and do that. Okay, so this is equal 2 times, and in parentheses, 1 minus, then start to type in NOR, and it'll find the function for you. Make sure you choose the correct one, double click on it. Then the Z, which is the absolute value of Z, which is 1.6, and then the word true. Now we use 2 parentheses, one for closing around this, and then one for the original parenthesis, and then hit equal. And this time is about 1.109599. Okay. Now, so we compare to alpha. Okay, and this time we see that the p-value is larger than alpha because 0.109599, of course, is larger than 0.05. Remember, alpha was not for 95%, is 0.05. Okay, so in this case, we do not reject the null hypothesis. Okay, what that means is that basically there's not enough statistical evidence to say that this, didn't happen by chance. That, if we assume this is correct, we assume that 53% of Americans would vote. So the claim was that the percentage is not 53%. Okay, so we didn't really care if it was larger or greater. The claim was that it was not equal to 50%. And here, our sample we got, even though 45% is less, there's not enough evidence to say that didn't happen by chance. It's not unlikely enough that we can say that it's most likely incorrect. Okay, so we do not reject HO. And so for our summary, then, just say something like not enough evidence to support the claim. And you can even put in, what more details about the claim. So the claim was that the percent of Americans who would vote for the incumbent president is not 53%. And simply there's not enough evidence to support that claim. It doesn't mean that the 50% would, it just means there's not enough evidence to say that there's a difference. And also like say, so in this case, at 95% confidence. Okay. As you can see, basically this cutoff here is for about 10%. Okay, so 10% something that can happen 10% of the time is not incredibly unlikely. That's like one out of 10 times. Okay, where something happens like 5% of the time, something happens like 1 out of 20 times or 5 out of 100 times, it's less likely. Okay, so that's the idea. And if you see in future videos, we'll actually do more examples like this. Okay. Now, last thing I want to talk about in today's video are about what are called type 1 and type 2 errors. And we've already kind of hinted at these, we just haven't defined them. Let's talk about that. So a type 1 error, let's just read this, the error of rejecting the null hypothesis when it's actually true. This is the most serious error in hypothesis testing. In our justice system, this is similar to sending an innocent person to prison. The probability of committing a type 1 error is alpha. If the consequence of committing a type 1 error is severe, alpha should be made very small. So what it's saying is that, like in the justice system, we consider that the worst thing to happen is to send an innocent person to prison, even worse than not sending a guilty person to prison. Okay, that's what's called a type 1 error. A justice system is designed to avoid that. That's why you say you're assumed innocent and proven guilty, whether you're actually innocent or not. Now, a type 2 error, then, is the error of failing to reject the null hypothesis when it's actually false. In our justice system, this would be the failure to convict a guilty person. Okay, it's going to be a lesser of the two types of errors. The probability of committing a type 1 error is called beta. Now, we're not going to talk as much about the type 1 error or beta. We're going to focus more on the alpha. Okay, but as it says, if the consequences of committing a type 1 error is severe, alpha should be made very small. And that's the reason we're using alpha like 95% or 99%, something like that. You probably want to use like 80%, because then 80% will only be like 1 out of 5, which is not that uncommon. Also, another good example is think about a company that makes drugs. So think about like the companies that made the vaccines for COVID. Obviously, they want their vaccines to be successful, and so we'd have a claim that this particular vaccine works, and then you'd have to go through a testing process and do kind of also hypothesis testing. So the null hypothesis would be that it doesn't work or has no effect. The alternate hypothesis would be that it does actually have an effect. It does actually vaccinate people. And then the same way, you want your alpha to be small, because what you really don't want to do is to claim the drug actually works and have it to not work very well or much at all. Okay, so finally, let's talk about type 1 and type 2 errors. So over here on the right, we have a couple claims and want to explain, based in words, what the type 2 and type 1 errors would be. Okay, in this case, it might be helpful to kind of write out the hypotheses here. All right, So these are the claims. A portion of people with blue eyes is equal to 0.35. Okay. Now this is another one where the claim would actually be the same as the null hypothesis, which is a little strange, but we'll talk about it. Okay. So all says word proportion, so it's going to be proportion P. And the alternate in this case is actually, the claim is actually the same as the null hypothesis, which is equal to 0.35. The alternate would then be that it's not equal to 0.35. Okay. So then a type 1 error for this situation would be to reject HO when the proportion is 0.35. Okay. Or basically to reject the null hypothesis when it's actually is true. That would be the type 1 error. That would be the worst error to make. Okay. Then the type 1 error, type 2 error. The type 2 error would be to not reject HO or to not reject HO. I apologize, my writing is not the best today. When the proportion, I would abbreviate that, is not equal to 0.35. In other words, we fail to support the claim. Okay. The type 1 error in this case would be to reject the null hypothesis when it's actually is true. Type 2 would be to reject it when the claim to not support the claim. So there actually is, the proportion of people with blue eyes is actually different from that, and we don't support that claim. Okay. So here I said not reject HO when proportion is not equal to that. And can also say failing to support, the claim when it's true. Okay, one more. Proportion of people who require no vision correction is less than 0.25. So once again, let's, for simplicity, write our hypotheses again. Null and the alternate. It's about proportion again, so it says we're proportion. Okay. Now, maybe easier to do the alternate first. So require no vision is less than 0.25. And so then the null hypothesis would be that's equal to 0.25. Okay. So the type 1 error would be to reject, or you can put this in maybe slightly different wording, reject HO, or also say support the claim, to support the claim. When the claim is false. Okay, so you support the idea that the portion requires no vision correction is less than 25%. Well, that's not true. Okay, and that would be like sending an innocent person to jail. Okay, then the type 2 error would be to fail to support the claim. So fail to support the claim when the claim is true. Okay, so fail to support the claim when the claim is true. This would be like this would be like in the justice system, be like not convicting a guilty person. Okay, because remember, so a type 1 error is like convicting an innocent person. The type 2 error is like failing to convict a guilty person. And we usually in our justice system, like hypothesis testing, then usually consider the type 1 error to be the worst error. And then generally you want to make sure then your alpha is small, so to make the possibility or the probability of committing a type 1 error also small. So today we summarized hypothesis testing, what hypotheses are statistically, then looked at basically how to test them, and then also how to kind of explain the results you get. Thank you. Have a good day.